All right, good morning, everyone. So, promised you we would do a review on the material we've covered so far. So that's what we'll do today. And I'll post everything I'm going to write down. So feel free, if you don't want to write down all this stuff furiously today, you can sit back and listen. Okay, so we'll start with units 1 and 2. So here the main goal is that we have a model that's linear. So we say we have the target y is approximately equal to intercept term plus beta 1 x all the way through beta dx d. And we call our estimate of y, we call that y hat. And there's the training phase where we fit the parameters, and for this we have we collect our training labels in a vector. We'll call this y bar. We're saying that these are approximately equal to, and then we put our training features, put our training features into a matrix, and then we multiply that matrix by our adjustable coefficients. So we'll call this matrix A, this is the vector B, this is Y, and we call the predictions here y hat 1 through y hat n, and call that y bar hat. Okay, so that's the training model. And then we have the testing model. We can say that y hat, as a function of just, we'll consider, actually, it's going to be a vector x. This is going to be, take the one scalar, we put it next to the vector x, transpose, and we multiply this by beta, and we usually choose beta to minimize the RSS. And so what is this RSS? RSS is, this is a function of beta now. This is the sum over our training samples, difference between the squared target and its prediction. Or if we want to write this as a norm, we could write this as y minus a times the beta vector squared. And so this is, we can also say this is a least squares problem. And to find the beta hat that solves this least squares problem, what we do is we take the partial derivative with respect to each of the beta j's of RSS, and if we evaluate that at beta j hat, that should equal 0. And when we work out all the equations, we find that beta hat is A transpose A inverse times A transpose Y. Just like that. So now when we measure the performance, we often think about R squared, called the coefficient of termination. And this is defined as 1 minus 1 over n times RSS over sy squared. And let's see. So when r squared is 1, that's perfect. When r squared is 0, this is a trivial estimator. And when r squared is less than 0, we would say this is impossible on training data for the least squares estimator. Okay. And feel free to stop me if you guys have questions on anything. Okay, but on the test, samples, it is possible to get a negative r squared, and you guys saw that, especially on the lab for Unit 4. Okay, so another thing we talked about is categorical features. So these are things like xj and abc, where abc are not numbers, they're not ordered. And we said to use one-hot coding. And in one-hot coding, we turn xj into a one-hot binary vector. And we have a couple options. We can code the intercept. Where each category gets a unique intercept, or we could code the slope. And then in this case, each category gets a unique slope. And finally, we saw an application to polynomial regression, where we said that y is approximately equal to beta 0 plus beta 1x plus beta 2x squared, and so on, all the way to beta dx to the power d. So what we're doing here is we're using x sub j equal x to the power j. And the main question that we asked here is how do we choose d? So that brought us to the next unit on model order selection. Okay, is everybody caught up? Those who are copying down? Okay. All right. So next unit was Unit 3. And so here we had a concept of underfitting, overfitting. Let's draw some pictures. So on the left, we'll do underfitting. On the right, we'll do overfitting. And let's draw some points. Okay, so in underfitting, we make a model that is too simple for the data set. In overfitting, we make a model, let's try again. Something like this. Maybe we fit all the points perfectly, but that is not what we want because we're modeling the noise. And then I'll say good fit in the middle. We want to do something like this. And so the question is how do we get that good fit? So the first thing we considered is let's look at the training RSS or MSE. And what we saw is if you plot either one versus model order D, you get something, you get a line that is non-increasing. And then so this, if you use this to choose your model order, I suggest to use the most complicated model of all the ones you've tested, and this leads to overfitting. So we don't want that. So the solution is cross-validation. And we'll say that you test, or maybe I'll say it this way. Design model order on samples different from the training samples. So we had a couple options. So one option was test, train, split, where we split the data into two different partitions. And the other was k-fold cross-validation, where what you do is you train on k-1 folds, test on the remaining fold, and then repeat for all combinations. Okay, so when we do this last one, okay. So yeah, when we do this last one with RSS, we can get something like the following. If we take the estimate of the RSS first of all, we do this for each model order hypothesis D. For each D, we compute k different RSS estimates from our different folds, and then we can get the sample average of that. And this is going to be for every hypothesis D. And we can think about this. This is an estimate of some unknown quantity which we would like to estimate, which is the statistical average of the RSS as a function of D. But in general, we don't know any distributions, so we cannot compute this. So we have to try to estimate it. So we can estimate the sample mean using this sample average. And then as one option, could then choose D, or let's just say choose D min is the arg min over D of RSS bar D. So that's one option. But RSSD is itself imperfect. Or maybe to be more explicit, imperfect estimate of the thing we would really like to know, which is the statistical average. So we can quantify the error. So we look at the standard error as a function of D. And the standard error is defined as, we'll write this as sigma hat over K. And where sigma hat is going to be computed like this. It's the square root of the sample, the unbiased sample standard deviation computed like that. This is unbiased sample. Okay, so this is the unbiased sample variance, and then we take the square root to get that sigma hat, which we use in the standard error estimate. So another way of thinking about this standard error is basically the variance of this RSS D minus its mean, the square root of that variance. So when we saw this when we derived the sample estimate of the variance, and actually I'm being redundant here. We can, sorry about this, we can actually remove, we don't need to have this in there, because the sample mean is unbiased. Okay, so that's what this standard error is. And the last thing we talked about is the one standard error rule. And this is a way of choosing D, is we let's see, so we have so the dots are the RSS bar D, so we're plotting as a function of D. And then we have the these standard errors are plus and minus standard error D. And let's see, we got one more over here. And so we look at D min, which is here, and we look at the top of its error bar, and we call this the R target. Let's see, RSS target, RSS bar target. And so in an equation, RSS bar target is RSS bar at D min plus the standard error at D min. And then we look for the simplest model. The one standard error rule is arg min over D of the D that gives RSS bar D less than RSS bar target. Okay, so we find the simplest or smallest D whose RSS bar is less than this value. So simpler D would mean we go this way, and here we see, okay, these Ds are simpler, but this D has an RSS bar which is below the target, and then this D has an RSS bar which is above the target. So for the one standard error rule, we would choose this one. Okay. And yeah, so this, just want to emphasize over here, this is the simplest model. So sometimes when we do our optimization over a variable like alpha, where larger alpha means a simpler model, then we have to take that into account. We would be looking for a maximum D, or maximum alpha. Okay. Any questions so far? All right. Okay, next concept was the bias variance trade-off. Okay, so for this, we have to establish our model. So we have a true model, y equals some function of vector x plus a noise epsilon, and that would be, let's say, for the test, and then for the training, looks the same, except we have subscript i's things. And for prediction, we're going to use, okay, we're making a prediction of y, but we're going to use a different model. We'll call it f hat. And this is going to take in the test features, but it's also going to take in some parameters that we have designed from some training data. So, okay, so let's see. So in terms of random quantities, we're going to think of all these as random. And let's emphasize that b hat is random because it depends on random training features and training errors. Regarding our errors, epsilon and epsilon I are IID with mean of 0 and variance or squared epsilon on average being sigma squared. Yeah, and this i's go from 1 to n. Okay, so I think that's our model. And our metric we care about is mean squared error. This is going to be a function of x, and it's the mean squared error on y hat. So this is going to be expected value of y minus y hat squared. And of course, y hat is a function of x. So that's why mean squared error is going to be, one other important thing, sorry about this. I have to condition that expectation on x. Okay, and this conditioning is because for now I want to hold x fixed so that I can see what happens for specific different values of x. Okay, so we did a derivation, and we found that the MSE on y hat as a function of x, according to the above model, is going to be sigma squared plus the bias on y hat as a function of x, that quantity squared, plus the variance on y hat as a function of x. So the bias is going to be expected value of the difference between y and y hat as a function of x. And then the variance is going to be, by definition of variance, this is going to be expected value of y hat. Actually, I guess the bias, maybe I'll change the sign on the bias. Put the y hat on the left. Okay. All right, so the variance is going to be y hat minus expected value of y hat given x. That quantity squared given x. So the bias measures whether our predictions agree with the truth on average for a fixed x hat, whereas the variance doesn't look at the truth at all. It just looks at the average squared difference between our predictions and their average value, again, for a fixed value of x. So when we make a plot of these things, we have model complexity like D on the horizontal axis. We find that the bias, the squared bias, tends to decrease, and the variance tends to increase. And the mean squared error is the sum of those two things plus the irreducible error. Okay, and then the last thing we talked about was special case of least squares linear regression. And we saw that when D, the assumed model order, is less than the true model order, we saw that the bias is not equal to 0. And we call this biased, and this leads to underfitting. On the other hand, if D is greater to or equal to D true, then we saw that the bias is equal to 0. And finally, we saw that we look at the variance on y hat as a function of x, and then we take an expectation over that x so that the result no longer depends on x. And then finally we get this very nice answer that the variance is d plus 1 over n times sigma squared. So the more features you have for a fixed training data size, the worse your variance gets. Or if you fix your features and you can enlarge your data set, your variance goes down, your mean squared error goes down as a result as well. Okay. So that's, I think, the main points on bias variance trade-off. Any questions on this? Good? Okay. So the last thing we have to talk about then is Unit 4. the theme is feature selection, which means we want to choose the best subset of features. So we talked about several different approaches. Exhaustive search, you just try all the subsets. You use cross-validation to measure their performance. This is optimal, but complexity scales as 2 to the power d for d features, so that is not possible for many problems. So we have stepwise regression. This is a greedy method, it's not optimal. But useful. And in this method, the complexity scales as just D alone. If you have D features, you just try D different model orders, essentially. Another option we discussed briefly is ranking based on it should be univariate statistics. For example, like correlation. So here the idea is picking features that are most correlated with target. This is a suboptimal approach. I have not found that it works very well, but maybe in the right application it works okay. And then we have the regularization based methods, which we spent most of our time discussing. So one approach, let's say the main one for feature selection we talked about is lasso. So we find the minimizing beta vector where you look at the sum of the RSS plus alpha times the one norm of the beta vector. So this is what we call L1 regularization. And so what we know about lasso is that it sets a subset of B to 0, but it also shrinks the remaining non-zero B, non-zero beta. So what we do is we use the subset of non-zero beta j, but not their values. And what do we do with that subset is we fit a least squares model. Okay, the other thing we talked about was ridge regression. So we have our RSS, then we add squared 2 norm. This is our L2 regularization. And this is not useful for feature selection because it does not give us zero valued beta j, but it is useful for correlated features. So in the last lab, hopefully you saw this, because what happened was even after you do lasso and you find the best subset of features, you can still improve the performance estimate if you, instead of fitting a least squares model, you fit a ridge model, which adds this. And in that, the application in lab 4, the features are very correlated, so this had a good effect on the test RSS or the test MSE. Okay, so those are the main ideas in terms of the feature selection methods. And then the last thing we talked about was the maximum likelihood, or we'll say the probabilistic interpretations. So the first was maximum likelihood. And maximum likelihood, what we do is we set beta hat, we call it beta hat ML. This is the argmax probability of y given beta. So this is, we think of y as fixed data. This thing we think of then as the likelihood. And we can also write this as argmin of negative natural log of the likelihood. One example of this, we saw that ML estimation of beta under the model y equal ax plus epsilon, where epsilon are Gaussian, zero mean, white noise, if you apply maximum likelihood to this model, you get least squares estimation. So it explains what we had proposed to do heuristically in units 1 and 2. Another application was, the map estimator, maximum a posteriori. So map is arg max beta, and then we swap the order here. We have probability of beta given y, and can also do arg min. Sorry, I forgot the little betas before. Arg min over beta of negative log probability of beta given y. And a couple examples here is ridge is maybe I'll switch to a thinner pencil. Okay, ridge is map under the model yi is xi transpose beta plus epsilon I, where epsilon I before is Gaussian with 0 mean sigma squared IID, and then beta j is Gaussian with 0 mean and some variance v, also IID. So again, this is the same model we used here, stated in a slightly different way. And then this is new if we assume that before we measure any y's, any data, we assume that we know our parameters are Gaussian, 0 mean and a certain variance. Then we do this math estimation, out comes the ridge solution. So the final thing is lasso is map under a similar model. So here we're going to have the same model for y. But for beta, we have Laplacian with some scale factor v. Okay, so these are all IID. Oops, I got lasso. Okay. Okay, so that concludes all the main points in these units. Of course, there's a lot of other small details that are in the notes. Any questions on anything we reviewed today? Yeah.
For the maximum likelihood, you want to maximize by selecting proper data, you want to maximize the probability of getting the y. But for the MAP, you want to maximize the probability of getting beta.
Yes, that's right. So in the maximum likelihood case, we're maximizing the probability of y given beta. And in the map case, we're maximizing the probability of beta given y.
What is the optimal beta, the
optimal according to this metric. So if you say, you could say they're the most probable beta. This is finding the most probable beta, whereas this is finding the beta such that the y's you received are the most probable. You're changing the model, you're adjusting the model so that the y's you achieved are most probable. So it's like you're moving the model around until the peak occurs at the data you observed. So one big difference is, in this case, you do not need any probabilistic model for the betas. Betas are essentially just deterministic parameters. Over here, we need a probabilistic model for the betas. And so that's why we have maybe a Gaussian or a Laplacian. But in this, what's nice about maximum likelihood is you don't need any model for the parameters. Parameters are just deterministic variables you can adjust. The only model you have here is a model for the data, so that the targets given the features.
By base rule here, we could write like P of beta given y is equal to P of y given beta multiplied by P of beta. Yes.
So let's see. So what we have is we can use Bayes' rule to say probability beta given y is probability y given beta times probability of beta over probability of y. So yeah, if I want to maximize this over beta, I can forget about the denominator. So I need to maximize the product of my likelihood and my prior. And in the maximum likelihood case, I'm only maximizing the probability of the likelihood. I have no prior. Yeah. So that's the distinction. You could say, they're both approaches as to what is optimal. I don't know that, if someone wants to advocate this, they'll say optimal in the maximum likelihood sense. It's almost like a definition of optimality. And then this is another definition of optimality. So one is not necessarily better than the others. They're just different approaches, but they're all principled in that they, they're well-defined, they make sense. Whereas something like least squares works great if your errors are Gaussian, but it works terribly if you have errors that are very heavy-tailed, like outliers. And so you could complain, well, least squares is a heuristic technique, and it can be misapplied. If you really know a statistical model, you can do much better than least squares. You can choose something appropriate for those kinds of errors.
We need to find the PDF of the data first, and then we can use.
Yes. Yeah. In fact, so another thing, I guess I haven't been completely consistent. So another way we could write this is we could put in the x's here as well. I have not been writing them explicitly, but they are there. So we could put x's everywhere. But yes, we do need this. We need this model. So here, even here, we're treating the features as deterministic, and we need the model that relates. We think of the targets as random, and we say, what's the distribution of these targets given the features and the model parameters? That's what we need. So, common models, for regression, the most common model would be Gaussian noise, additive white Gaussian noise. Another model would be replace this additive noise with something that has heavier tails than a Gaussian, like you could use this Laplacian model. And the Laplacian model has heavier tails, which accounts for outliers that are farther from the norm than Gaussian. And if you replace this with Laplacian, you would find that instead of doing least squares, you would be minimizing the L1 norm of the difference between y and y hat. That would be the solution.
Data set is the input. Yeah. Our data is the input for our model. Why we consider that Gaussian?
So again, this, if we want to make a statistical relationship between x and y, we need something that adds randomness, right? Because if I told you that there was no noise here that says y is exactly equal to ax, and in any data set where y is not equal to ax, you would immediately know that this is not a good model. So we need to account for the differences between our targets and, actually, sorry, there's a mistake here. This should be x beta. Sorry about that. Okay, so here we have x, here we have beta. Okay, so if I don't account for the differences between y and beta, I cannot come up with a good explanation of my data, because in general, my targets are not a perfect fit to any model parameters. So I need to have some sort of way to capture the difference between those two. And so putting an additive error in here is common, and then I need to choose a distribution on those errors. And the Gaussian is a very common distribution. It's very tractable. It's very easy to work with. But I'm saying that it may not be a good model for some data sets. So you may want to instead assume something like Laplacian errors, which are more heavy-tailed, which handle outliers better. And if you did that, and if you followed the maximum likelihood procedure, you would find that instead of minimizing sum of squares, you'd be minimizing sum of absolute values, which ends up being the L1 minimizer. And it's a convex problem, and you can solve it, and you can find those betas, and they will work better for some data sets. But it all comes down to your choice, your assumption on the errors. That's the way maximum likelihood works, and that's the freedom we have, as we can choose. Essentially we're choosing this model here. That's what we choose. When we go to map, we have one extra thing we can choose, which is the distribution of the betas themselves. So now we have two different things. We can choose the data distribution and the parameter distribution, and we can use both in our fitting. But yeah, this is super important, so I'm glad you guys are asking these questions. All right, any other questions? All right, great. So please, if you have more questions, don't hesitate to ask. Put them in the discussion section on Carmen. And exam is on Friday, so on Wednesday we'll come back to our lecture on optimization, and then Friday we'll have the exam. All right, see you guys next time.